Hi everyone, welcome back to Math 111. This is Scott. Let's get started. What we're going to be doing now is cracking open a new chapter. So this is the last chapter that we'll be dealing with, and the first section of it is section 6.1, where we will learn about exponential functions. So first off, the format. So an exponential function has a formula in the form f of t equals a times b to the t. So the important thing about this is that the variable is in the exponent. The variable is in the exponent. So what that means is the factor of b is how much is going to be changing as t steps up. So these represent functions whose value changes by a certain consistent percentage or fraction, same thing, just expressed differently. Fraction, ratio, factor, by a certain consistent percentage or fraction, ratio, factor, things like that, etc. Per unit time. Per unit of time. So this is not, so it's not things that change by a certain amount each time. So it's not things that change by a certain amount, but certain fraction. Not things that change by a certain amount. It has to be a proportion. It changes by. So for example, so it's not things that change by a certain amount, but it has to be a certain proportion. So for example, exponential or not. So we'll look at a couple scenarios and decide, is it an exponential function or not? Exponential or not? First one, let's say we have a population increases by 25% every 2 years. So this is yes. It perfectly fits the description of an exponential function. It's increasing by a fixed amount, or by a fixed proportion, namely 25% each 2 years. Now, as a counter example, let's take something like an account grows by, let's say, $100 every month. So this is an example of a note. It's going up by a certain amount, not by a certain factor. No. Amount. Not a factor, not a percent, not a decimal. How about something like the number of infected individuals doubles each 3 years, or every 3 years. So again, by saying doubles, we're saying that it is going up by a certain fixed proportion or ratio. So yes, it again matches the description. So now, back to the format. So f of t is equal to a times b to the t. Let's figure out what these things each represent. So if t equals 0, then this is an exponent of 0. And things raised to a power of 0 just make 1. So then this would just equal a. Now the meaning of each of the pieces is, therefore, that a is the initial amount when t is equal to 0. When t equals 0. So that's what a stands for. Now as for b, b is the amount that the function gets multiplied by each unit of time. So this is what's called the growth or decay factor. This is the growth or decay factor. So this is the factor the quantity gets multiplied by. Each unit of t that passes. So we are talking about things that are growing or shrinking by a certain factor, by a certain proportion, by a certain ratio. Now what b actually represents then is whatever rate it's growing by plus 1, because b represents how many there will be next year compared with how many there are this year as a factor. So this represents this year, and then this represents the growth, the actual growth rate. So r is the growth rate, or decay rate if negative. So what this means is that if b is bigger than 1, it's growing by that factor. So it's convenient also sometimes to rearrange this and write it as b minus 1. So take off the 1, and that'll tell you how the thing is growing or shrinking. And I should note that r is the growth rate as a decimal or fraction. So what that means is that if b is greater than 1, then we have exponential growth. So if b is greater than 1, we are in an exponential growth scenario. If b is less than 1, then we're in exponential decay. Next section will look more precisely at the actual graphical situation, but for now I should just note that exponential growth is like that. Exponential decay looks like the same thing but in reverse. And one note: b is never 0 or negative. So b always has to be positive. You can't lose more than you actually had from one year to the next. Okay, now quick check here. Exponential growth, exponential decay, or neither? Exponential growth, decay, or neither? So first, let's take something like y equals 200 times 1 plus t to the power of 7. So first off, is this exponential growth, decay, or neither? Well, looking at this, it has an exponent, but that's not what makes or breaks an exponential function. Exponential functions do not mean functions that have exponents. They mean functions whose variables are the exponent. So this is not an exponential function. So the answer is neither. And in fact, actually, this technically is a polynomial. It's polynomial, in fact. So it's not an exponential function at all. Okay, well, what about if we had something like y equals 20 times 1.09 to the t? So this is an exponential function, and because b is greater than 1, it is exponential growth. Exponential growth. And in fact, we can say more. We can say what the starting value was. We can say what the growth rate actually was. So it starts with 20 at t equals 0. And it grows 9% each unit of time. And that's the meaning of the 1.09. So b equals 1.09, which implies that r is that minus 1, so that's just going to be the 0.09. In other words, 9%. And now for another example, let's take something like this. Let's go y equals 25 times 0.88 to the x. So it can be x or t, either way. So here now we again are in an exponential format. This fits the profile of an exponential function perfectly. But the b is 0.88, which means that r is 0.88 minus 1, which is negative 0.12, which means that it is decaying because it's negative. So this is exponential decay. But we can say more. We can say what it starts at. So it starts at 25, and it loses 12% each unit time. Now here's another example. We could have specific populations of things and compare them. So let's say we have two populations. Say a of t is equal to, let's say 100 times 1.07 to the t, and let's say b of t is equal to 20 times 1.16 to the t. Okay, now we can ask and answer some various questions about this. So, A. Which population is growing faster? So notice they are both growing. So which population is growing faster? Well, there are two numbers in play here. This is the A, the starting amount, and this is the B, the growth factor. And the one with the higher growth factor has the faster growth. So population B is growing 16%. And I should say T is years. Population B is growing 16% per year, which is faster than A, which grows 7% per year. Now, if you wanted to actually answer some more questions about this, you could plug in actual numbers. So, what are the two populations after 3 years? and that would just mean plugging in the 3. Now for the case, so that would mean plugging in the 3, and in the case of A, that means that we would be talking about 100 times 1.07 to the third, which you can evaluate on a calculator, and any kind of calculator will do. For example, something like this will do it. Desmos can do it. Anything can do it. And you would just put in, you don't need those parentheses, they're not actually really accomplishing anything. And you put in all the pieces and you get an answer of 122.5, we'll just round it there, versus B of 3, which equals 20 times 1.16 to the third, which we can evaluate same way. And so I'll round it there. Round it the same precision as I rounded the other one. So A started off bigger. It was 100 to start with. B was 20 to start with. But 1 year later, and 1 year later, or sorry, 3 years later, A is still bigger. But we can take it out further, and let's say, what about when t equals, and here we could say, for example, 30. Instead of 3, 30. So now, A of 30 would be 100 times 1.07 to the 30th, which will equal 761.2, and B of 30 will equal 20, 1.16 to the 30th, and you'll notice that now 1716.99, so really I should round that. If I'm going to round it to the nearest tenth, it's going to be 1717.0. And so, although A started off being much bigger, after a long enough time span, B ended up bigger. So note, even though A had a larger initial population, (100 versus 20), B eventually grew larger than A, and this will always happen. If you have any group that has any two groups that are both growing, the one with a higher growth rate will eventually outstrip the other one. So there's that. Alright, now that's the end of phase 1 of section 6.1, but now it's time for us to really get into the nitty-gritty of the math of it. So finding Finding formulas. For exponential functions. Alright, so this is going to come in a spectrum from easier to harder. And the easiest version of this kind of question is going to be one where the information is basically going to be spelled out for us. So the easiest kind is, so phase 1, info given to us. For example, I might tell you what the initial population was and how much it was growing, or the initial amount of money and how much it was growing. So for example, we could have something like a starting population, of 300, and let's say it decreases 2% each year. So then that tells you right off the bat, A is 300, decreases 2%. So that means R is negative 0.02, which means that B is going to be 1 minus 0.02. So B is what you keep if you lose 2%. So that's going to be 0.98. So this is the easiest kind. The second iteration of this is going to be the harder kind. So second way we can have to go about this is we are given 2 points. And have to find A and B ourselves. Okay, so here's the basic idea behind this. So once again, things can be a little bit harder or things can be a little bit easier. First off, pay attention if either of the points happens to be the y-intercept, because if it is, then that actually saves you a little bit of work. So if one of the points is the y-intercept, that gives the value of A. All right, so that's one thing to look out for. It could be could get lucky, and we could actually have the y-intercept as one of our 2 points. But no matter what, finding the b is going to be a little bit of a hassle. But here's how to find the b. Finding b. So set up the equations y1 equals a times b to the power of x1, or t1, doesn't matter, and y2 is equal to a times b to the power of x2. And then, once we have these set up, basically we can just do a division. Divide the two equations and use the properties of exponents to try to solve for the b. So then, divide the two equations and you'll we'll have y1 divided by y2 is equal to a times b to the x1 over a times b to the x2. And then use the properties of exponents to solve for b. So notice the a's are just going to cancel each other right away, and so we'll have y1 over y2 is equal to, now it's what we're doing is we're dividing two different exponents, or two different exponential expressions with b, so that actually just has the effect of subtracting the exponents, x1 minus x2. Etc. And then you'll have an exponent on b, and then you will just raise each, then raise each side to the power 1 over x1 minus x2 to isolate the b. Alright, now let's actually, and then, so then we'll have the b. Do not actually round this. Do not round until the very end. Do not round until the very end. Okay, so not until the very end of the operation. Then, if we don't already have a, so if we still need a, so namely if one of the points wasn't already the y-intercept, then we can solve for a. Solve for it by plugging one of the 2 points into y equals a times b to the x. So put in the y value and the x value from one of the 2 points, either one, whichever one you think will be easier. Okay, this is a kind of complicated sounding procedure. Is it going to turn out to be complicated? Well, the only way to tell about that is with an example. And now for our first example, let's take the following. So, find a formula for the exponential function through each pair. Through each pair of points. So let's start with the pair 0, 5 and 2, 180. All right, so here we have to start with one of the points being the y-intercept. So this is the y-intercept, which means, because the x value is 0, which means 0, 5 tells us what the actual a is. So a is 5. Okay, that's nice. Now then, if I wanted to do the y2 equals a times b to the power of x2, and the y1 equals a times b to the power of x1, what that's going to lead me to is, well, we've got a y of 5, we've got an a of 5, we've got b to the 0, and on the other side we've got 180 and 5 and b to the second. Let those cancel each other, and so what I've got is 5 over 180 is equal to b to the 0 minus 2. But these actually have a common factor of 5, so this is actually 1 over 36 is equal to b to the negative 2. So then I raise both sides to the negative 1/2. Equals b. And so I've got my formula. So once I've got my formula, I can just actually go ahead and evaluate the b at the end. So if I still had to find my y, my value of a, I would wait to do any rounding, should any rounding prove to be necessary. But we need to put this into a calculator, and just for safety here, let's make a note of what we would need the parentheses to be here in order to do this properly on a calculator. Otherwise, it will be all messed up. So b equals that, which will equal 1 divided by 36, and you may already know what the answer is going to be because these are some special numbers. But if not, you can just let the calculator do the work for you and find an answer of 6. So you put the formula together and you've got f of t, or f of x, or whichever way you want to put it. F of x equals 5 times 6 to the t. So that's how that goes. Let's try another one where the a is not actually told to us. So now let's try one like this. So the points will be -1, comma, 144, and +1, comma, 100. So we are not currently told the a, so it's up to us. Well, we do have the x's and y's, so let's just go ahead and use those. So 144 equals a times b to the -1. 100 equals a times b to the 1. Divide these. And what we'll have, again, ordinarily I wouldn't go too far on evaluating these. I would leave them as fractions if I had to. But because this works out so nicely, we might as well go ahead and take advantage of that. Now the a's cancel each other, and so what we've got is b to the power of -2. And once again, that means we're going to raise each side to the power of -1/2. So you do what you have to do to cancel that. So b is equal to 1.44 to the 1/2. And leave that unevaluated until we have the a. So then to find the a, we can use either of the two. I shy away from the negatives just by instinct. So 100 is the y. A is a mystery. 1.44 to the negative 1/2 to the 1. But these would just multiply, so it's easy to see what it is raised to the 1, but if it had been something else, those would just multiply together. And basically what that just gives us is a equals 100 divided by all of that. And if I were evaluating that in a calculator, I don't want to take any chances here. I would want to put parentheses and such around that. Not that I need them in this case, but you know, the numbers don't always work out so nicely, so we'll see in a second that the numbers can be a lot messier. So this is how you can enter it in any case. And so we can finally find out how things are going to be here. So then so for the b, that's 1.44 to the power of negative 1/2. And that's going to be 0.8333. So b is equal to 0.833333. And 3's repeat, so you can use the repeat bar. As for the a, that equals, and you can just let the calculator do the talking for you unless you feel like getting clever. 1.44 to the power of negative 1/2. Oops, negative 1/2 times 1. So here again, a lot of silliness in writing it all that way, but I just wanted to have it in the most general way it could be, so that way we don't have to. So that way we have a procedure that'll work even when things work out nicely or when things work out poorly. So that means f of t is equal to 120 times 0.833. So the way your book recommends this is it says 4 decimal places on its eventual answers, and it can do a t or an x. But what you can't do is both. I just made a blunder on the previous problem. I realized have to pick a lane, x or t, x or t. Let's go t. X or t. Can't have a mix and match. A mix and match function has to be either t's or x's. I couldn't decide, so I did the wrong thing. And for this, we'll say for this whole section, when on all these sorts of problems, round to 4 decimal places. On final answer. Okay. Now let's do one where it doesn't work out so neatly. So these two have worked out pretty nicely, but that won't always be the case. So let's see what it looks like if it's just helter-skelter bad numbers. So we could have something like 3, 150 as one point, and then as a second point, we could have 10, 1000. So nothing convenient here as far as being given an A or anything like that. So we just go straight for it. Y2. And we have mystery A. We have B to the 10. Sorry, the reason I keep doing the Y2 first is by habit, I like to put the bigger number on top of the smaller number. There's no advantage to that though, so I left myself room here. I can put the Y1 on top of that, just to keep consistent with the notes. It's the kind of thing where my habit is to do it one way, but my official policy is to do it a different way. Math gives it a lot more scope for freedom than people usually give it credit for. Anyway, so here we have a place for the A's to cancel. Here, actually, we could simplify that, or you know what? Why bother? So there are common factors that they share. You can obviously tell that they're both divisible by 10, but in fact they're both divisible by 50. Actually, I was being all catty about it, but why not? We divide them both by 50. That's going to be a 3, and that's going to be a 20. Okay, and then over here it's going to be b to the 3 minus 10. So in other words, we're going to have 3 over 20 is equal to b to the negative 7th. And so then what that means is that b is going to be 3 divided by 20 to the power of negative 1 over 7. So it's raised both sides to the negative 1/7 power, the reciprocal of this. Okay, so that's going to be what it's going to be, but I'm not going to actually evaluate that yet until such time as I have my A and I'm ready to go forward with that. So now to find the A, you take one of the 2 points and you plug it in. So 150 is equal to mystery A times the not so mysterious B. And again, this is a very messy way of writing it, but no harm in that. As long as you have a method that works. You don't need to necessarily always make it the best it can be, but you might as well turn that into a product. So 3 times negative 1/7 is going to be negative 3/7. Negative 3/7, and divided by over here as well. And so A equals, and there's nothing rounded here. This is all exact. And the beauty of that is, then at the end we can round to our heart's delight. Actually, I should even keep doing it in the calculator fashion because I don't want you to miss a parenthesis on the calculator because that can be a big issue. So then B is approximately, so we'll go ahead and evaluate that one, 3 divided by 20 to the power, you definitely need those parentheses, otherwise you are in trouble. So it's negative 3/20 to the power of negative 1/7. That's going to give us our B. And that gives us 1.3113 if I go to 4 decimal places. And then for the A, That's the same numbers except 150 divided by 3/20ths to the power of negative 3/7. And we have 66.5254. 4 decimal places again. And so that gives me our f of t is equal to 66.5254 times 1.3113 to the t. Now, I should say there are some other ways of doing this that are a little bit more elegant, but a little bit less of a straight line approach. So if you see one of those while you're out and about on the internet, or somebody shows you some other way, you can go ahead and use it. Just as long as you do it some way that is correct. That's all I care about. All right. Now, let's take a look at things from the table perspective. So tables. And in particular, this is going to be true if tables go up by 1 each. So if a table of values represents an exponential function, so if a table of values represents an exponential function, regular increments of x will correspond to consistent ratios of y. And in particular, if the x values go up by 1, then b will be y2 divided by y1. If the x values go up by anything other than 1, then you can just basically use the same approach as we did with the points, but the problems that you'll be seeing will have x values going up by 1. Then we can find a by plugging in a point and solving. So, for example, and a note on this, if a table is not an exponential function, we might also be interested in whether it is a linear function, and what that means is a function that goes up by the same amount each increment of x's. So note, if a table is a linear function, so if a table is a linear function, the y values change by a consistent amount. Rather than a consistent factor. So let's try our luck. So first off, the kind of examples that we'll see will look like this. So example, exponential linear or neither, and then a follow-up question, if it is exponential, find a formula. All right. So here's what we have to look at in these. So we'll have a table, and the table might be something like this. So we'll have x values, and then we'll have f of x values. 1, 2, 3, 4. And then the f of x values will be something like, let's say it is 5, 10, 20, 40. 5, 10, 20, 40. So first off, just looking at this, we can already actually have a good guess as to what's going on here. And in particular, we can see that the y values appear to be doubling with each step of the x. So we might actually be able to jump to an immediate conclusion here, but just to be consistent, let's look at the ratios of the y values. And in particular, it's y2 over y1. So in other words, later y divided by earlier y. So 10 over 5. 20, so that's the same as just 2. 20 over 10, which is again just the same as 2. And then finally 40 over 20, which is again 2. And because they're all the same, that means it's exponential. It's exponential, and in particular, it's exponential with a b value of 2. So that's half the formula right there. F of x is equal to a mystery a times 2 to the x. All right. Well, then plug in one of the points, and we can find the a. So 5 is equal to a times 2 to the 1. So in other words, 5 equals a times 2. Divide both sides by 2, and you get a equals 5 divided by 2. And that leaves us with a formula, f of x is equal to 5 over 2 times 2 to the x. So this is what it looks like when it is an exponential function, and this is how you would go about it. Now, if it is a linear, then what you would observe is something like this. So f of x. 1, 2, 3, 4. And we'd have something like, let's say, 80, 73, 66, and then lastly 59. Now you may have noticed the pattern here, and the amount of change, in other words, change in y, y2 minus y1, is going to be 73 minus 80, which equals -7. 66 minus 73, which is going to equal -7. And then 59 minus 66, which equals -7. So that means it is linear. And now for part C. For part C, what we have will be something like this: x, f of x, 1, 2, 3, and 4. And maybe it's going to be something like 7, 10, 15, 22. So if we look at the ratios, y2 divided by y1 is going to be 10 divided by 7, 15 divided by 10, 22 divided by 15, and I don't have to be a genius of division to know that these aren't all the same. So not exponential. And then amounts. The amounts of change, y2 minus y1. So those are going to be 10 minus 7, which equals 3. 15 minus 10, which equals 5. And 22 minus 15, which equals 7. And they're not all the same. So, not linear. Linear means a straight line. Straight lines just go up by the same amount each time. This doesn't do that, so it's not linear, not exponential, which means it is neither. Okay. Now, here is a common application of exponential functions, and it is what is known as compound interest. So the setup. Setup here is you have a fund, or maybe it's a debt, but we'll just say a fund. A fund with balance A of t, where t is in years. So as a function of time, time is in years. So then some of the ingredients. P stands for the principal, which is the initial amount deposited in the fund. Then R. This represents what is called the nominal interest rate, sometimes called the APR, but this is as a decimal. And then N represents the number of times the interest is generated or compounded per year. So for example, if the interest is compounded, let's say first off annually, that would mean once per year, so N would be 1. Let's say it was semi-annually. That means every half year, so that means N equals 2. Quarterly would mean 4 times a year, so that would mean N equals 4. Then maybe, and then the next big one would be something like monthly. That means 12 times a year, once each month. So N equals 12. Weekly, N equals 52. Oops, F. And then the furthest we'll go on this is daily, which would mean N equals 365 times a year, even though, so this would be what we typically use for a calendar year, a usual calendar year, even though some years have 366 days, such as this one. Then the formula. The formula that will tell us how much is in the account will go like this. A of t is equal to the initial deposit. So it's playing the same role as initial amount does in usual exponential functions. And then 1 plus, and this may look a little familiar because this is just like what happens in the relationship between b and r. B, the factor, is 1 plus r. Here, though, what is changed is that the r is going to be broken up into smaller payments. Namely, it's going to be broken into n pieces each year. And then it's going to be raised to nt instead of just t. And the significance of this is that the n is, so the n is not only cutting down the size of each interest payment, but it's increasing the number of interest payments. So if you're getting 12 times as many payments, that's up there, they're each going to be 1/12 the size. So, for example, let's just say something like, invest $200 at 1.5% interest. Compounded monthly. 10 years. So the principal here would be 200. The rate is 0.15%, so it's going to be 0.15 if we do it as a decimal. People often think of it as moving the decimal 2 spots over. Personally, I think that's a little bit. I don't really like that particular way of thinking about it. I prefer actually just remembering that the hundredths place is the ones for the percents. And then N is the monthly, so that's 12, and then T here is going to be 10 years. 10 years down the line. And so A of 10 will be, sorry, we'll just put in the actual numbers here. A of 10 will be 200 times 1 plus 0.015 divided by 12 to the power of, and no harm in putting parentheses here, 12 times 10. And so that's going to equal, and you just do this all in a calculator or Desmos or whatever means you typically calculate by. And 1 plus 0.015 divided by 12 into the parentheses to the power of 12 times 10. Make sure there are parentheses there, or else actually do the multiplication. And we would get $232.35. And because we're talking about dollars and cents, we would round it typically at the hundredths place, because that's the smallest that the denominations of US dollars are typically broken down. And different examples, we'll just be changing different numbers. Okay. Now, there's also a different way of expressing exponential growth, and that is with the continuous rate. So exponential growth and decay with a continuous rate R. So this is an alternative way of expressing exponential growth, and the key word here is continuous. The continuous is the giveaway. So the ingredient here is something first off called Euler's number. And it's pronounced Euler, like as in the Houston Oilers, but spelled E-U-L-E-R. And Euler's number is represented with an E, and what it actually means is not really, so that'll come out in the after a bit of use. But what its value is it's 2.71828, and then the digits keep on going forever. But just like pi, the digits go on forever. They don't settle down into any predictable pattern, and they just keep on chugging. So this is a number. It is the base that is used for continuous growth rate. So Euler's number is this, and we use this as a base for continuous exponential growth models. And particular, the way the formula will look is it'll be f of t is equal to a times e to the rt, where r is the continuous growth rate, with the continuous rate of r. So if r is positive, then that will mean it's growing. If r is negative, that will mean it is shrinking. If r is positive, this means exponential growth. If r is negative, then exponential decay. Now, in the case of compound interest, rather than compounding it yearly or monthly or weekly or daily or hourly or minutely or secondly, we can compound it continuously, which means instant by instant. So continuously compounded interest. So this means moment by moment. So this is compounded each instant. The formula for that is that the amount is equal to the principal still times e to the rt, and this represents the absolute extreme when it comes to compounding. So for example, so let's take as an example a case of, or first let's look at what continuously compounded exponential functions are and what they aren't. So, is each of the following an example of a continuous exponential growth model a continuous exponential decay model, or neither. And let's start with something like y equals 2000 e to the 1.4 t. So right up here, that's where the r is. This fits the model, and the r is positive. R is bigger than 0, which means continuous exponential growth. And on the other hand, we can look at something like y equals 300 times e to the negative 0.05 t. And here the r, so the r was equal to 1.4 in the first one. Here the r is equal to negative 0.05, so r is less than 0, which means continuous exponential decay. And then example C, let's say y equals 10e to the 100 over t. So at first, this looks like it's the right format, but it actually isn't. So the t is not in the right spot. The t should be times, not multiplied, or not divided by. So this is not in correct form, which means this is not exponential growth or decay. It's something else. Neither continuous exponential growth nor decay. It's got its own thing going on. All right, and then the next task is to actually use the continuously compounded interest model. So let's say we invest $300 at 5%, 5% continuously compounded interest for, let's say, 7 years. So the formula here is A of t equals 300, now it's e 0.05 t, and we'd want to plug in 7 to that. Now, on any scientific calculator, you can find the e, and it will look like e to the x. So let me zoom in on that if I can. E to the x is what it will look like. So right here, it usually shares a button with ln, which you'll see why later on in this class, a couple weeks from now. But it's the same. So it's e to the x. And on Desmos, you can just use the letter E, and it also works. So then, the way we would enter something like this into a calculator would be 300 times e to the power of 0.05 times 7, and you hit enter, and you'd have 425.72. And this was money, so it should be dollars. Another thing that you can have to do is evaluate some other types of expressions in a calculator, and when you do, make sure that you're very careful with parentheses. Evaluating exponential expressions in a calculator. And by calculator, I'm including here Desmos, Be careful about parentheses. Watch parentheses carefully. So for example, let's say f of x is equal to something like 2 minus 5 to the power of negative 3 x plus 1, and we wanted to evaluate f of, let's say, negative 2. Let's make it more interesting. Let's make it f of negative 1/2. All right. So we just got to be very, very careful here. So f of negative 1/2. Let's just go ahead and put this in the way we would have to enter it into a calculator. So 2 minus 5 to the power of, and then here, negative 3, and then you'd want to make sure that you put parentheses very carefully around this part, plus the 1, and then into those parentheses. Any of these parentheses go missing, and you're going to end up with some trouble. And then just evaluate it. Just let the calculator do the work. Just relax and lean back, and the calculator will do your bidding. So it's 5 to the power of negative 3. Make sure you use the proper negative button, not the subtraction button. So negative 3 times, and you can put in the times or leave it off on this. Some calculators, though, will be a little bit pickier about that. You'll have to know your own device. Plus 1, parenthesis, and you get the number approximately negative 53.9017, rounding it to 4 decimal places, which is what your book does throughout most of this section, except for the money problems. Okay, so there's that. And now the last task of the day is going to be in real-world applications. So applications. So the way these are typically going to work is they'll come in 2 stages. Stage 1, you have to find a formula given the information that they give you. In stage 2, you're going to have to figure out what the other piece of information that they want is. So there are going to be 2 stages. Stage 1. Find a formula using the given information. And here we'll use the previous techniques. And stage 2 will be to use the formula to answer the question. Alright, let's just peel the band-aid off, see what this can look like. Example. A town has a population of, let's say, 15,000 in the year 2000. And then, let's see, in 2010, the population had grown to 25,000. If this growth continued, in an exponential manner, what would it be in 2020? Alright, so let's think about what we've got here. So we've got some years, we've got some populations. So years and populations, that's the information that's given to us. And here, there's no reason why we can't do it in thousands. So the information, in the year 2000, the population was 15,000. In the year 2010, the population was 25,000. In the year 2020, that's what we are out to find out. Now, let's say we can choose anything we want for what the t represents, and we can say the t represents years after 2000. It's often convenient to take something, take a convenient starting point as the initial value. So that makes the points 0 for 0 years after 2000, and then and 15,000 is the population, and then 10 and 25 is the next point. So here we are now back on firm footing. We've got what we want from the setup here. We've got 2 points, and one of them even gives us directly the a, because it's the y-intercept. Okay, well then what that means is that we can take the 15 and the 25. That's going to be equal to the a times b to the 0 and a times b to the 10, so just the same thing we were doing before. And so that's going to be a common factor of 3, so that's going to be, sorry, common factor of 5 I mean to say, and so that's going to be 3 over 5 is equal to b to the 0 minus 10. Just transcribing that. So these have the common factor of 5. That's going to make a 3 and a 5. So then, b to the negative 10 is equal to 3/5. So I raise both sides to the negative 1/10 to isolate the b. So b equals 3/5 to the negative 1/10. And so here now we can evaluate this to get the yearly growth factor that we are experiencing in this little town, and that's going to equal 3/5 to the power of, oops, almost forgot parentheses, would have been a disaster. 3/5 to the power of parentheses, parentheses, parentheses. That's the key. If you're using the calculator for any of this. 1.0524, which by the way means that the R here is 0.0524, just skim off the 1, and that means it's growing 5.24% growth per year. Not that that was asked of us, but no harm in noting it. But then the question is, what is going to be the population in the year 2020? So f of 20, so f of t is equal to, the a we were told was 15, 1.0524 to the t, and then f of 20 will be, so then we calculate that, 15 times 1.0524 to the power of 20, and that gives us f of 20 is approximately 41.658, so 6, 6. So again, we were measuring in thousands, so there's no, so it's kind of silly to go too far in precision. So f of 20 is about 41.66. So we can say something like the population will be about 42,000 by 2020. So it would be about 42,000 by 2020, according to that model. All right. One last application here. Let's say that what we have is something like this. Let's say that 50 grams of a substance decays to, let's see, 27 grams after 10 minutes. And now let's say that we have several questions that follow up on this. The first one, let's say, is something like, what is the percent decay each minute? So what that's really asking for is the R. That's what this really wants. So what is R? Okay, well, once again, what we've got are a couple of points. And what we have is time and quantity. And this is minutes, and this is grams. So when it started, there were 50. Then 10 minutes later, it was down to 27. So we once again got a good setup here. 0, 50, 10, 27. Well, looking at this, we can see that a is 50 because it's the y-intercept. Now 50 and 27 are the y1 and y2, and then a times b to the 0 and a times b to the 10 are right here. And we just divide them, cancel those. 50 over 27 is the same as b to the 0 minus 10, which means 50 divided by 27 is the same as b to the negative 10th, which means b is equal to, and you notice these calculations are all going down the same pathway each time. Negative 1/10. And so, if we actually calculate this, remember our parentheses, 50 divided by 27 to the power of negative 1/10. Remember parentheses, 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 parentheses. And that gives us 0.94024. Just put a bunch of decimal places on there. Now r is equal to b minus 1. So that means r here is going to be 0.94024 minus 1, which is negative 0.05976. So it loses 5.976, I'm sorry, like that, percent each minute. Now, the final question that we might be asked on something like this is to then use the formula to figure out how much will be left at some future point in time. Oops. How much would be left after 1 hour? So let's see. So putting the pieces together, we already know that f of t is equal to 50 was the a that we found, and the b we scratched together 0.94024 to the power of t, and here it would be asking us 60 minutes down the road for 1 hour. So that's going to be 50 times 0.94024 to the power of 60. Alright, so now we play the calculating game. 50 times 0.94024 to the 60th power. And what we find is that if it's going to be losing so much every 10 minutes, then by the end of an hour, 1.2396, it'll be down to a small fraction of what it started with. In particular, it'll be 1.23. I would say 1.24 grams, just rounding it randomly, after 1 hour. Okay, Well, that's the end of that section. A lot covered there, a lot of ground covered. And we'll be picking it up again next class to look at things like the graphs of exponential functions. And then later we'll explore some more stuff involving exponential functions and their inverses. But until then, I'll see you later. Bye.